Okay, hello everyone. My name is Chen, and today it's my great pleasure to give a keynote about our recent understanding in terms of element of learning systems. As we all know that we are in an interesting area of machine learning where the software landscape start to change from what we traditionally believe. So traditionally, when we start to think about building softwares, we want to try to build a wide range of applications that works on a limited set of software libraries. And then, it's like a small funnel. And as we start to trying to build, things on a small set of applications, and then they need to run on certain kind of general purpose computing platforms. The interesting thing about the traditional software landscape is that we are normally aiming for broader coverage, where computing performance is less critical, and engineers normally handles most of the optimizations of your applications. In the area of machine learning, we start to see this paradigm shift, where in the front end, we start to care a lot more about applications that involve things like machine learning models, which will need to take a large amount of data in order to build their capabilities. And on the back end, we start to see that we will need to be able to run those models on a diverse set of compute, including things like data center CPUs, GPUs, mobile devices, Raspberry Pis, and sometimes our computing backend could involve a cluster of specialized devices. This shift really makes it important for us to rethink, what are the necessary means we can build to support the age of AI software landscape. And these new characteristics also brings new challenges on how we want to build new softwares and solutions for future AI applications. So today we are going to focus on this particular area inspired by this change. Namely, we're going to focus on the area called machine learning system, where those systems are trying to combine and unify the efforts of the computing resources, the large data set, as well as the machine learning models to really bring in these machine learning models and machine learning methods accessible to the production workload. In the past few years of my development, actually, I'm lucky enough to be involved with a group of open source community working on quite a few successful learning systems that are out there being widely deployed. And today I'm going to tell you a bit about lessons we learned from some of our past learning systems and some of our systems we're developing right now. The two systems I'm going to talk about are XGBoost, which is a gradient tree boosting system that brings data science for everyone, and TVM, which is a system that helps us to deploy AI everywhere. So, and to recap, in terms of learning systems, we're going to touch the following key perspectives. The modern learning system will need to be accessible to general audience and scalable to a wider range of computing resources. And secondly, in the context of TVM, I'm going to tell you a bit about, how can we bring intelligence to the learning system, as well as how can we build the system so that it can take fully advantage of the full stack design, including systems and software and modeling. So I'm going to start with the accessibility and scalability angle. And to begin with, I'm going to tell you a bit about our lessons learned when building XGBoost. So if you don't know what XGBoost is a scalable system for learning gradient tree boosting ensembles. So those gradient decision trees are very useful ways for us to pick up signals from our incoming data set and try to bring accurate predictions about things we are interested in. Sometimes it can be things like, healthcare risk prediction, stock market prediction, loan default prediction, or in the case of more recent, being able to track what are the effectiveness and correlation between COVID-related healthcare tasks. We built XGBoost around 2006, and since then, it has become a de facto tool for data scientists to build their learning solutions, and has been used by more than half of our Kaggle-winning solutions, and has been used in scientific endeavors such as discovery of Higgs boson. And since then, it also has been used by a lot of major companies and enjoys quite a lot of tractions in terms of open source community. So when we start to look at the success element of XGBoost, there are several key improvements that we have been built into XGBoost itself. In terms of machine learning algorithm, we try to introduce an automatic way to handle missing value modeling and ways to allow us to speed up sparse learning of trees on sparse data. On a system perspectives, we're also bringing in new techniques that help us to make a system cache aware and make use of the storage SSD available in my system. I'm going to give you a quick overview of how one of the key features in XGBoost, and that is how can we handle missing values. In a lot of cases, when we are trying to looking at a data set, a traditional way that data scientists assume in a traditional textbook setting is that your data is being perfect. The reality is that in a lot of cases we will find data that are missing. Sometimes it is due to imperfect collection of data, and some other times simply due to the nature of the data set itself. And traditionally, data scientists will have to deal with those missing data by either manually impute the data in some way or trying to be able to cleaning up the data in a customized fashion. However, that has never been an easy task. So one of the things that XGBoost tries to do is actually trying to remove that burden from a data scientist and be able to build models that can automatically handle unknown or missing values. In this particular case, for two of the missing values, in the tree learning process, besides introducing the classification rules of each of the decision nodes, we're also introducing what we call a default direction, which will indicate where the classification will go if you encounter a missing value. More importantly, we want to be able to jointly learn the default direction as part of the tree learning procedure. Intuitively, that's somewhat equivalent to automatically learning to impute a missing value based on the data set distribution without having a human to intervene. The advantage of this automatic missing value handling method is that data scientists now no longer have to worry about how do you handle missing values. And this is one of the major reasons XGBoost being widely adopted, because this makes the method really be accessible to a larger, broader audience out there. The second thing we have been working hard on XGBoost is trying to make it platform agnostic. When I'm starting to look at distributed learning platforms, for example, usually some of the platforms will have specific implementation that are especially tied to the platform themselves. When building XGBoost, we really want to make a generic abstraction that allows us to depend on a generic reusable abstractions and making the system portable to a lot of platforms. Because of the design, it's really great to see that you can run XGBoost in any of the languages that you like, as well as any of the platforms you like. Since it's Ray Summit, I've heard from the folks that Ray also can't start to bring in support for XGBoost, and it's really great to see a move on that end. So we have talked a bit about the scalability and accessibility angle. Let me switch gear to talk about the other angle, which is how can we deploy machine learning algorithm or AI algorithm to everywhere? In particularly, we start to see a challenge of deploying machine learning models on a wider range of hardware backends, including things like CPUs, GPUs, embedded devices, and specialized accelerators. The main challenge of such kind of deployment is that it brings quite a lot of engineering challenges to show you what's happening nowadays. Today, when we're trying to deploy machine learning models, we're trying to rely on what we call machine learning frameworks, where typically each of a machine learning framework will represent the computation of interest in what they call a high-level data flow graphs, where each of the node of the graph correspond to a high-dimensional tensor operator. For example, in the case of a convolutional neural network, a node can correspond to a conv2D operator. In order to offload these data flow graphs onto a specific kind of hardware, for example, in the case of NVIDIA GPU, we will need to offload those computations into some heavily hand-optimized libraries that implement those computing primitives. The problem of this approach is that for each of the color nodes there and one kind of hardware backend we're interested in, these color nodes have to exist in a low-level library. Additionally, this will translate to human engineers and engineering teams in the hardware vendor companies or in the application companies to having to implement those primitives. And if you are familiar with machine learning system optimization, you might say that hey, I want to continue and improve this computational data flow graph. For example, one thing that people can do is try to take two nodes and try to fuse them together. In this case, or in other cases where we want to be able to develop new models, new machine learning operators are being introduced. That means that we want to be able to hire more engineers to be able to implement those additional nodes on the low-level library. If we want to multiply that by the amount of hardware backends such as CPU, GPU, and Raspberry Pi and accelerators we want to implement, you can imagine that it's very engineering intensive. That is why I want to take a completely new approach to bridge this gap. The idea is that instead of trying to use humans to bridge this gap of high-level machine learning model and low-level hardware backends, we try to develop an automated algorithm that makes use of machine learning to automatically directly generate optimized programs for new workloads and hardware backends. To give a sense, how we do it, the idea is that for each of the color nodes there, we're going to express the computation in some specification form that specifies the computation in high level. Then for a given specification, we're going to define a search space of possible program optimizations that maps to different low-level program variants. Note that there can be many different kind of ways to implement a particular specification using a low-level program. For example, we could directly implement this transpose matrix multiplication using a vanilla for loop. We can also try to transform a loop a bit so that you can get better cache locality. So usually this kind of code works better on CPU. Or if you're interested in a specialized accelerator that contains special instructions such as DMA copy and matrix multiplication, we want to map some of our code to the accelerator instructions that help us to accelerate the computation. So the idea is that there are a lot of optimization choices to optimize operator specifications. And the question we are facing is that how can we explore these billions of possible optimization choices to find a good one that allows us to map those high-level computation on the hardware target of interest. In order to do that, we can formalize this problem as what we call a search problem. Let's use E to denote a specification and S of E to denote a search space. The goal of AutoTVM, which is our action, is trying to generate an optimized configuration that we can then send to a code generator, where the code generator can measure the execution time and use that to minimize our end-to-end execution. The key idea in AutoTVM is we want to be able to leverage machine learning to do that. Specifically, we want to be able to generate different configurations for a target hardware, use those measurements to collect training data that allows us to learn a statistical cost model that predicts cost of a given configuration without having to run it through the real hardware. The idea is that by using statistical cost models, we can quickly try out different kind of configurations without having to actually do real-world benchmarking and walk through the space of billions of possible choices very quickly to find out the good solution. Additionally, we're also constantly updating the statistical cost model along the way while we are trying to generate new configurations sent to the target hardware. By leveraging this statistical-based approach, it allows us to automatically adapt the code generation process to the specific hardware type. Because as we start to collect data profiles on the hardware of interest, the statistical cost model is going to pick up the properties such as cache lines and other things without having us to annotate those properties to the system. And the system will be able to automatically adapt to the particular hardware and being able to generate code that accelerates that hardware. Of course, one of the things that we always want to ask, how can we construct such a search space that optimize for different hardwares? And in here, we are trying to build our idea on previous solutions such as Halide that allows us to build possible mappings from high-level expressions to low-level valid hardware programs. And the question really there is, how do we define such a comprehensive search space? So on CPUs, we are reusing a lot of the previous knowledges, such as doing loop transformation, optimize for cache locality, and make use of vectorized instructions on the low-level CPU. And things become mostly interesting when we start to think about a heterogeneous amount of hardware, including data center GPUs and TPU-like special accelerator. I'm going to touch briefly on the search space for specialized accelerator because they are really interesting, both in terms of the both in terms of the instruction they expose, as well as the memory subsystem those accelerators gives you. In terms of compute primitives, if you look at the traditional CPU and the traditional, so what you will find is that normally the instruction we have and when we program them are scalar programs that specifies how do you compute each element of the target data. And as we start to look at modern CPUs start to introduce vector instructions that allows you to compute, say, 4 floating points or 8 integer numbers in a single cycle instruction. That brings a bit more challenges in terms of how do you structure a program. If you start to look at TPU-like accelerators or NVIDIA's Volta, those hardwares start to contain high-dimensional tensor instructions that allows you to do, say, matrix multiplication or convolution in a single cycle. And this really creates challenges for a system because different hardware backends have different kind of hardware backend primitives. And it's really hard for us to build a system that allows us to support these kind of emerging tensor instructions without knowing them beforehand. In order to do that, what we are trying to build is what we call building a tensorialization engine that allows us to take a compute specification as well as a hardware interface specification that specifies the behavior of low-level hardware. And the goal of the tensorialization is to be able to take the high-level compute specification as well as hardware interface specification to jointly transform and map the high-level programs to make use of the specified hardware interface. In TVM, we have some semi-automatic solutions that supports tensorialization process, and there's an active effort on trying to build automatic solution on top of that. As a result, TVM is an end-to-end machine learning optimizer that allows us to be able to take high-level models and offload to various kind of hardware backends, including CPU backend, CUDA, and different kind of GPUs, and even web assemblies and DSPs and microcontrollers. To give you a sense, what we can do by bringing this kind of automated solution, let me show you a case study that we have done on 16 on different kind of models and hardware combinations. When we're trying to run the ML compilation on these models, we start to find that we can get a lot of interesting speedups, in particularly on some of the models that our customers are interested in. This is because in a lot of cases, when we're looking at standard benchmarks, a lot of the standard libraries are heavily optimized for standard benchmarks because that was the goal of those employees in those companies. On the other hand, a lot of the interesting models people are looking at are non-standard, which are not very well optimized by the standard library approach. By using automatic ML compilation, we can automatically get better speedups on those non-standard models in a much faster fashion because we can look at the specific hardware platform and model and specialize for them. Additionally, it also allows to be able to bring in immediate hardware support for new hardware, such as Apple's M1 in day 0. And in this case, we are also getting better solutions than Apple's native approach. Finally, I would like to mention that TVM is now a top-level Apache open source project, and you are more than welcome to join the community to work together as well as develop together as a Apache community. With that, I would like to conclude my talk. Today, we have talked about 3 kind of important elements of a learning system. Through XGBoost, we learned that it's important to build learning systems that are accessible and scalable. Through TVM, we know that it's important to build intelligent automations and full-stack solution. A combination of all those elements will be able to enable a lot of the useful lessons for future learning systems. With that, I would like to conclude and thank you very much.